Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Okay, welcome everyone, and thank you for joining us today. I'm Shiji Jiang from Max Planck Institute for Biochemistry, Germany, and it's my pleasure to welcome you all to the AI for Good webinar series. Our speaker today is Dr. Kelsey Dockson. She is a postdoc jointly appointed at Arizona State University School of Computing and Augmented Intelligence and at the University of Cape Town's Climate Risk Lab, where she leads the agricultural impacts research pillar. Kelsey completed her PhD in the computer science at the University of Oxford, where she developed applied machine learning tools for Earth system science in collaboration with NASA's Jet Propulsion Lab, the United Nations, and the European Space Agency's PhilLab. And her current work focuses on using Earth observation data and artificial intelligence for climate research, disaster preparedness, and humanitarian applications. And welcome, Kelsey. And for our audiences, before we begin, just a quick reminder, if you have any questions during the talk, please post them in the neural network and we'll return to them in the Q&A session at the end. And now, Kelsey, the floor is yours, and we are looking forward to your talk.
Thank you so much. All right, I'll get started with first sharing my screen. So good morning, good afternoon. Hello, everyone from wherever in the world you are connecting from. I'm currently in Arizona, so it's the morning time for me. And I'm really happy to share my work on AI for humanity using Earth observation for solving global challenges. So I'm going to first start with some of the research motivations and objectives. The work I'm sharing today is going to be from my PhD work at Oxford, and specifically highlighting two projects focusing on humanitarian capacity building and talking a little bit about operationalizing AI as it pertains to disaster preparedness. So overall, my work is to develop and leverage AI tools for the purpose of tackling complex Earth science problems. These are related to climate change, natural hazards, and humanitarian applications. And I've divided my research work as a part of my PhD into three of these interrelated pillars, being climate, which I won't focus on today, but happy to discuss at another time, disaster preparedness, and humanitarian capacity building focused on the global south. So to get started, I want to talk about the first project, which is a part of UNICEF and ITU's Giga Initiative, which was an initiative to connect every school to the internet and every young person to information, opportunity, and choice. And this work is in support of the SDG 4, quality education, to ensure inclusive and equitable quality education and promote lifelong learning opportunities for all. This was a really unique collaboration at my time at the ESA PhilLab between the European Space Agency, UNICEF, and ITU, as well as at Oxford. So to provide a little bit of context about the Giga Initiative and the project itself, I'm going to start first with an overview of this. So in December 2020, the United Nations Children's Fund and ITU reported that 2/3, or 1.3 billion, of the world's school-age children do not have internet connection in their homes. And so to combat this, Giga was created, aiming to connect every school to the internet and thereby every young person to information, opportunity, and choice. I mean, we can think about it ourselves, especially when we consider how the world has changed so dramatically from the COVID-19 pandemic as it pertains to online education. If students aren't able to access internet when they're at school, folks are going to be left behind. And so to tackle this, Giga was created. And what we're specifically tackling is something called the digital divide. So the digital divide can be thought of as the disparity between countries, regions, and people and their access to digital services. In 2023, 60% of the African population, or sorry, 60% of the African population is unconnected to the global digital society. And in the United Nations designated least developed countries, less than 30% of the population uses internet, according to a 2021 estimate. So there is enormous disparity between digital access in developing regions as opposed to other regions in the world. Over 500 million students worldwide don't have access to the internet. And this is also not only a digital access disparity problem, but also a gender access problem. Africa has one of the world's widest digital gender gaps, 35% versus 24% male to female in 2020. So we're trying to aim to tackle this digital divide and create an equitable solution to providing internet connectivity in schools. So how do we do this? How do we promote internet connectivity in schools? This comes to our first two research questions. The first is, can we use remote sensing based machine learning methods for poverty mapping context and apply this instead to internet connectivity mapping in the African context? And further to that, can we use existing satellite embedding data sets or foundation models, as it's frequently referred to as well in the AI community, to predict internet connectivity, specifically in Botswana and Rwanda? So we have two pilot countries that we're focusing on in this work, Botswana and Rwanda, but this also could be extended to other countries around the world as part of UNICEF's global community. But first, I wanted to start with, I usually, if I'm doing this talk in person, I ask for some audience participation, but I know folks are either online or watching this at a later date. So I'll just give a minute to pause and folks can think to themselves and ask the question, what do connected schools look like? If we want to use geospatial data to predict whether or not we think a school is connected to the internet, what does it actually look like when we're looking at this satellite imagery itself? So I'll take a minute. Pause. Of these schools or images, what do you think are schools that are connected to the internet? And what do you think are schools that are not connected to the internet? And it's hard, right? Looking at this, it's extremely difficult to decipher. A lot of these pictures look very, very similar. So actually the top row that you're seeing of schools in Botswana and Rwanda, these are locations for which schools do have connectivity access and internet connectivity. And the bottom row of images represent schools or locations that do not have internet connectivity. So looking at this right away, it seems like a very difficult problem. And spoiler alert, it is a very difficult problem that I'll touch on briefly throughout this presentation. So what we want to do is use a plethora of different geospatial information, as well as census and ground-based data, to try to create a very rich set of features to be able to describe the ground conditions of whether or not we think that schools are going to be connected to the internet. And the reason why this problem exists at all, I think sometimes when I talk about this research work, the first question I get is often, how do countries or regions of the world, not know what regions are connected or not connected to the internet? And this is because ground-based surveys are very, very expensive. They can cost on the order of millions of dollars. If schools are located in more rural regions, it can be very difficult to get a full picture of a country's connectivity status or even where schools are actually located itself. And so we're trying to fill this gap by providing a way to predict connectivity from space. And just to give an idea of what the actual ground truth looks like that we're working with. So the data that we are using to train our machine learning models on is from Project Connect from UNICEF. So this is a global database of locations of school information, and it also provides information about whether or not a school is or is not connected to the internet. So in these two images, this is of Botswana and Rwanda, maps of the two countries. Green triangles represent school locations that are connected to the internet, and red circles represent locations that are not connected to the internet. I think one thing I want to mention is that this is potentially not a full record of the ground truth in the region, but this is from the stakeholders in the humanitarian country offices that we're working with to provide us with these school records. So this is the kind of most up-to-date records that we have, and we treat this as the ultimate source of truth when training our machine learning models. Okay, so to get a little bit more into the actual technicality of how we're doing this, what we're trying to do is leverage geospatial data in geographically aware models or foundation models to predict internet connectivity. And our problem setup at a very high level, we're doing binary classification task. We're trying to predict if a school is or is not connected to the internet. And we do this through two different methods that we investigated in our work. The first being using what we call engineered features, or more features that are a bit more interpretable. So in this case, we're using geospatial information like nighttime lights, global human settlement layer, MODIS land cover, population data, global human modification information, and creating a set of tabular features to feed into a machine learning classifier to make a final prediction. We also explored then location encoder beddings, which I'm going to talk about in the following few slides, so I won't go into too much detail now, where we're using pre-trained geographically aware models like SatClip. These create feature embeddings per location on Earth. So we do this over the location of the school, and we then use those as features into our machine learning classifiers to then predict if schools are connected or not connected to the internet. So the location embeddings are leveraging foundation models, which have been shown to perform really well in downstream tasks. However, they're a lot less interpretable as opposed to engineered features. So this is kind of a trade-off when we're considering implementation or deployment into operation and working with stakeholders. You're always going to have a trade-off of using kind of more black box features or black box models versus more traditional models that stakeholders can understand a little bit easier if they don't have extensive AI background knowledge. So to do this, I wanted to introduce a specific tool that was built prior to this project during my PhD, but it was used throughout this project and all of my research work to date. And this tool is called AirPy. So originally it was supported for a climate project, but I actually used this again during this internet connectivity project. So I wanted to highlight it here. It's a Python package to generate AI-ready datasets for geospatial studies, and it leverages Google Earth Engine. One thing I really like about Google Earth Engine, if folks have not used it before, is that it's free. And particularly when you're working in contexts around the world that don't have their own digital infrastructure or satellite constellations or very dense ground truth, Google Earth Engine or other free geospatial data sources is very valuable to build data sets to be used in geospatial studies. So how it works, very high level, for any latitude, longitude point on Earth specified by the user. So in this case, we specify the locations of the schools that we have from our UNICEF database. The AirPy package will download and process machine learning ready features from Google Earth Engine. So it currently supports a plethora of different products. We use the MODIS land cover information, world population data, VIIRS nightlight data, global human settlement layer, and global human modification. And it can also be saved in different formats. So this is more of this slide more acts as sort of a shout out to other AI developers that are interested in leveraging this type of tool. It's a really nice and easy way to be able to integrate geospatial data into your pipelines. And it decreases computation time from 6, 8, even 12 hours to around 40 minutes for the entire globe, depending on your data resolution. So this was a package that we used throughout our work to create geospatial feature products for our feature space. But one thing we had to consider as a part of our engineered or geospatial features was what was the actual radius of extent of information we wanted to extract surrounding a school. So the first step in our data processing pipeline was extracting the geospatial data and then understanding actually what was a good amount or too much or too little geospatial information that would provide context to support internet connectivity mapping. So these two images are showing school locations in two different regions in Botswana. A green triangle represents a connected school, and a red circle represents a unconnected school. And you can see here, they're actually quite close. These schools are around a 1 kilometer, if not closer, to one another. So the radii that we choose is actually quite important, because if we're choosing, for example, 5,000 meters, which is represented by the largest circle surrounding the center points, you can see they're going to have a lot of overlapping information between the 2 points, and this can confuse our model. So what we did as a first practice was essentially an experiment where we varied the buffer extent size, where we're extracting geospatial information from, and used that in the initial models to be able to decipher what was sort of our ideal or optimal buffer extent, so that we didn't have too much overlapping data, but still provided enough context such that it would be relevant into our feature space, particularly when you're thinking about different data sets that might have different spatial resolutions. There's always going to be a trade-off when you're considering how much information to take surrounding your school point. And so just to briefly kind of provide some results to our work. So we looked at 1,000, 2,000, 3,000, 4,000, and 5,000 meter buffer extents. We used a plethora of different machine learning models, gradient boosting, logistic regression, multi-layer perceptron, random forest, extreme gradient boosting, and SVM. And we ran our classifiers using different radius extents. And I think the main takeaway for this slide for folks is that as we increase in our buffer size, we actually decrease in our F1 score, relatively speaking, for both countries. But Rwanda is and was much more difficult. And I'll talk about this specifically a little bit later in other results because of the density of the schools relative to one another. Whereas we can see more clearly in Botswana, which is the BWA short form, that the F1 score and accuracy drops as we increase our buffer size. And this makes sense when we think about, again, the previous slide where we can see starting to get more overlap when you have larger buffer extents. So we wanted to minimize this. And so therefore we chose a 1,000 meter extent of geospatial information surrounding the schools and use this in our input feature space. Another piece of information that we use in our feature space is distance to transmission line network. So this is from a global power grid database that was originally formulated by Facebook, and it's a freely accessible product that you can use online. And so in QGIS, what we did was we overlaid the transmission line network, which is in yellow, and we mapped all of the schools. We didn't care about the relative connectivity status in this particular map. We just wanted to see the distance for all of the schools. And what we did is we calculated the distance to the transmission line network for each school. And sort of the methodology or reasoning behind this is the thoughts that, well, if a school is closer to the power grid, it's probably more likely to be connected to the internet than a school that's much more farther away from the power grid. You know, if you're already not connected to electricity, then your chances of having connection to the internet are much, much lower. And so we created this data set to integrate into our feature space as well. I just wanted to take a moment to note as well that I think when you're working in contexts where you have to leverage freely available data, you have to get quite creative. And so this is why we kind of use a big variety of different data sources to try to describe the ground conditions. One, because we wanted to leverage all the information we could. And two, internet connectivity is a very difficult problem to predict from space. It's a very complex downstream EO task. And so this was one of the other features that we included. And you can see there that some of the schools are quite close, some are a little bit farther, and this is the information that we used in meters. Okay, and so I did talk a little bit as well about the Geo Foundation model features that we included and explored. And so I wanted to talk about this as well before I showed some results. So this is incorporating what we call geographically aware models or foundation models for predicting internet connectivity. And the models that we used are CLIP, or contrastive language image pre-training models, where CLIP is normally trained on text and image pairs, Now these models are trained on location and image pairs. So this provides spatial context within the AI models using satellite imagery. And the encoders are trained to learn implicit representations of locations from satellite imagery. And one of the great things about these models is that they're trained on global databases. So ideally, they're quite generalizable to different regions of the world. A lot of the times when we're working in AI, I think folks that have done research in these fields can see that generalization is a big issue, particularly when you're training models, for example, on data from North America, and then you try to deploy it in areas like in Africa or South America or other regions that aren't included in the training space. Essentially, the models fail. So what we're doing is trying to include this GeoFoundation models via the CLIP location encoders to provide spatial context, but also more generalization. And so the 4 different models, as I mentioned, are the SatClip, GeoClip, CSP, and the ESA PHILAB very high resolution, or PhilEO very high resolution location encoders. So the vector embeddings themselves, they're extracted from images, and they can be thought of extremely small summaries of those images that claim to capture ground conditions, including population density, housing infrastructure, sun exposure, and more. So the idea is these embeddings, though they're not interpretable, they're capturing this contextual information that can support our models in understanding what the ground conditions surrounding a school are. So each location encoder used in our study is trained with a different data set. And the idea behind this is we wanted to explore the performance differences between the imagery sources. So we selected CSP for its pre-training on the functional map of the world data set, which was developed to predict the functional purpose of buildings and land use from satellite images. And also functional map of the world, they're grouped according to their purpose. And we thought that there's potential in delineating connectivity status from buildings, in our case, schools, by leveraging these embeddings. CSP is pre-trained from the iNaturalist data set, but we didn't explore this specific data set because it's not appropriate for our use case. So we focused on functional map of the world only. SatClip was selected because it's shown superior performance on other downstream tasks, and so we wanted to include it, and it uses Sentinel-2 imagery as well. We included GeoClip for its performance for folks we've seen work done achieved on their work in data limited settings. And then we also chose, of course, the PhilEO, the ESA PHILAB very high resolution data set, because it was one of the most state-of-the-art when we were developing this project about a year ago. It has around 50,000 points, very diverse, geographically diverse data set that we wanted to include as a part of our embedding space. And the embedding size just refers to the number of embeddings, or you can think of it, the length of the feature vector per point. So we have ranging embedding sizes as well that we include in our feature space. Okay, and so this table is very crowded, so I don't want to take too much time going through every single row or every single column. But the main takeaway from this is highlighted in the blue boxes, the cyan boxes that we have. So what we did is we looked at all of the SatClip pre-trained models with the varying ResNet sizes, as well as using the Vision Transformer VIT model as well. And we found that across the board, actually using engineered features, so those are those features that we calculated using that buffer extent, and in combination with the ESA PhilEO very high resolution embeddings, actually performed the best in terms of accuracy and F1 score, as opposed to just using embeddings on their own. And I mean, this isn't really a sort of shocking result. It sort of supports the claim that we sort of need these features in combination with more sort of interpretable and engineered features, because it's not enough to effectively tackle the complex downstream task of internet connectivity prediction. Already, this is a very complex task itself. And so the combination of embeddings and engineered features also provide model interpretability, which is again favored by users that are not within sort of the AI technical space. And when you're considering this in sort of a policy, informing policy and future decision making as to diverting resources and building infrastructure in different regions, you need to have some way to be able to effectively communicate what your results actually mean. It's not often enough just to have one thing be better if you can't actually describe it itself. So one thing we did to kind of further support that was look at using our random forest classifiers. So we use, as I mentioned, a bunch of different classifier architectures ranging from gradient boosting to random forest. And one thing that's really nice about random forest, if folks have used it at all, is of course its feature importance, which is a very easy way to be able to interpret what features or what pieces of information were valuable in making decisions for the model to predict connectivity in either connected or not connected. And so what we found is the global human settlement layer. This is what is GHSL. The built up characteristics and information surrounding that was very, very important. We also found that the distance to the transmission line network was actually ranked as third by the model in the Rwanda context was very interesting. Um, Kind of going back to what I mentioned at the very beginning when we were thinking about relating internet connectivity to poverty mapping, this is what's inspired us to select some of the different data sets like nightlight information. And we can see that this is shown by our model in both Botswana and Rwanda as being ranked as one of the higher features as well to provide some more information. And we know that poverty mapping and nightlight data has been used quite extensively in the past as well. So that sort of supports our claim that this can be related in some ways to that similar problem, and those methodologies can also be explored. Something else that we explored, though, however, is we wanted to be able to reduce the false positive rate and just overall increase our F1 and accuracy score. And so what we did was, in addition to those geospatial features and location embedding information, what other ground-based information can we use? In the beginning, we wanted to sort of step away from using ground-based information because we know, again, it's very expensive to do ground-based surveys. But if the data exists, you might as well leverage it as well. So what we did was from UNICEF, we had school education level as well as distance to LTE station and distance to UTM station. So these are related to mobile networks. As well as regional indicators, so actual administrative boundary information. And we included that as features into our models space as well to see if this would improve performance. And so this table shows Botswana, which is again short formed BWA, and Rwanda, RWA. And we can see there's a massive increase in performance, particularly when you look at the false positive rate, when we include that auxiliary information versus not including that auxiliary information. For example, using our extreme gradient boosting, we have a false positive rate of around 40%, which is extremely high. And that drops all the way down to 13% when we include that auxiliary information. Also looking at in Rwanda, we have a drop again from 64% in false positive rate to 26%. So this was a massive increase and kind of supports the claim as well that you need to include a very diverse and a very rich set of information in order to capture this complex downstream task. And I talked a few times about how Rwanda was particularly quite a difficult use case for our work. And so I wanted to highlight why that is a little bit more specifically with a case study in Kigali, Rwanda. So what this is showing is a high resolution imagery over the extent of Kigali, which is the capital city of Rwanda. And we have 4 different symbols. Green represent connective, circles represent model predictions, and triangles represent the ground truth of these schools. So I just took a random location within the city and zoomed in, and I wanted to look at, okay, let's look at 2 different regions in Kigali itself, and how close together are schools that are or are not connected. And you can see they're actually quite close to one another. All of these schools that I'm showing here within A and B are within 300 to 500 meters of one another. So when we're considering that we're using geospatial information, which is information surrounding the extent of the school, but the schools are super close to each other and do have differences in connectivity status, you're going to have this more increase of false positive rate, and the model is going to struggle. Even though our model, for example, in box A, our model predictions again are circles, so we can see our model predicted connected, connected, and again, connected, but this red triangle represents an unconnected school. Our model is learning in this region based on the geospatial information surrounding these schools that they are connected, but again, the ground truth says otherwise. So it's a very complex task. And, there could be many reasons that are not communicated to us as science researchers as to why the ground truth is represented how it is. Maybe there doesn't need to be connected in this school because there is maybe communication or collaboration between schools that are really close by to each other. We don't know. So we just have to use the ground truth that we have as a source of truth. But this is one of the reasons why, in particular, Rwanda was a very kind of difficult use case to start with. But it was a very fun challenge to see how far we could push kind of current existing foundation models and other geospatial data to tackle this task. Something else I wanted to talk about just before getting into a little bit more about the limitations and also to the final project I'll speak about today is the study of using, again, more sort of unique data sets, particularly when you're thinking about trying to use data sets that are either freely available or just different or unique, or might better represent internet connectivity itself. And so with UNICEF, they had an agreement with Mapbox, which is a company that can provide mobility data. You can kind of think of this as the number of cell phone pings to a satellite at any given location in time. And so what we wanted to do was a part of the Giga Initiative. We're looking at school connectivity mapping, but we're also looking at school mapping as well overall. And so we wanted to understand, is there differences in mobility data time series that we could use to delineate not only between schools, school connectivity, but also whether or not a location is actually a school or maybe it's, a different location. And so the idea behind this, or sort of the reasoning behind this is, I like the anecdote of comparing how busy is a school between 8 a.m. to 4 p.m. There's usually a couple spikes during the day. During drop off, maybe parents are dropping their children off, maybe during lunchtime, if again, parents are coming to pick up their kids, or maybe kids are leaving to go home for the day, things like that. And the end of the day as well, again, when there's sort of this pickup time, maybe the kids are being picked up by their parents or they're leaving, that's when you're going to have the kind of sort of changes in activity level. But when you consider another type of building that also inherently looks like a school from space, like a hospital, these are usually going to have peaks maybe throughout the entire day. They have very high activity level. They'll definitely be a lot busier on a weekend as opposed to a school. And so what we wanted to do was see if we can use time series information from this Mapbox mobility data to be able to delineate between schools and non-schools. And so this plot here is just showing a difference between the relative activity of a school versus a non-school, things like a hospital, police station, et cetera. And we can see that there are quite big differences between the two. I won't go into too much about the machine learning of it. This was more of a case study at the end of my work with the Giga Initiative, but I wanted to just drop a note of it because I thought it was a cool use case of data that we hadn't explored before. Okay, so in summary, I just wanted to summarize some limitations and future directions of the work. I think that one of the biggest limitations was label quality. So we have an unidentified latency between internet connection in a school and labeling. We don't know when a school has been connected to the internet other than when the data was given to us. So we treat that as the source of truth. So if I got the data on October 1st, 2023, I assume that is the latest information that we have, and that accurately represents the current conditions as of that date in the schools. There also can be inconsistency of label quality. We did our best to clean up this with removing things like duplicate points or schools that we didn't want to include, like, for example, preschool. We cared a little bit less about internet connectivity because that was sort of less impactful on education as opposed to secondary school. We also found that we did need auxiliary information in our models in order to improve model performance. So this was, again, including things like the school levels, as well as distance to LTE network or regional indicators. So ground-based survey information may be necessary to improve performance. We also saw, again, that the transmission line network information was quite valuable for both Botswana and Rwanda. Some of the future directions is looking actually at, instead of just binary classification of connection or not connection of internet, instead looking at connectivity quality and infrastructure. So identifying infrastructure to support digital capacity building. This will be interesting because you can already think about how you can build upon the pre-existing infrastructure in the region. Is it going to be fiber? Is it satellite dish? So that governments and policymakers can effectively divert resources accordingly. And then I showed this previously in the last slide, is looking at school mapping with human mobility data. So using that Mapbox mobility data for distinguishing building type, but then also using that as a complementary piece of information for school connectivity status. Okay, so I'm changing gears quite a bit, but I'm going to treat this more of a holistic view that can be related to both projects. So I wanted to now sort of switch gears a little bit and talk about another pillar of my research work from more of a sort of lessons learned perspective. And this was in the disaster preparedness pillar of my work, forecasting landslide impacts in Nepal. So this is really lessons learned from operationalizing AI. So the project that I was working on, I apologize, I can't show too many results because we're about to submit this for publication, but I wanted to talk about it because I think it's quite interesting and important when you're thinking about operationalizing AI in both the internet connectivity project, but also in a disaster preparedness context. And so what our project was aimed to do is predict landslides on a 14-day look-ahead window in Nepal. And what we were doing is leveraging pre-existing anticipatory and disaster preparedness infrastructure in the region to do this. So we were using records provided by the government of Nepal, Ministry of Home Affairs, via the BiPAD portal. This is a screenshot of what the BiPAD portal looks like. You can check it out if you just Google BiPAD Nepal. And it's a online database that shows records of a variety of different kind of natural disasters or risks or impacts and hazards in the region. We were focused just on landslides itself. And what we wanted to do was use these records along with geospatial data to create a operational tool that folks in the region could use to support anticipatory action during Nepal's monsoon season. So this is a season between June and September when the majority of landsliding occurs in the region. Currently, there does not exist a sort of sub-seasonal approach or 14-day approach to landslide forecasting. And so we wanted to provide this tool using the records from the BiPAD portal. This screenshot here of this table is just showing you what the data looks like when you actually download it from the website itself. So you download it as a CSV file, as an Excel CSV file, and we essentially used this CSV file as our source of truth and created an entire sort of pipeline to landslide impact forecasting. But I don't want to talk about the tech of it itself. I actually really want to talk about the lessons learned from it. And the first one that was one of the biggest takeaways, and that also, again, relates very much so to our internet connectivity project, is communication to stakeholders. If you want your research to be used, you need to be an effective communicator. It's really as simple as that. It doesn't matter how amazing your results are or how cool the model is or how innovative. If you cannot effectively communicate how your model or how your work is going to positively impact whatever problem you're trying to tackle, then it's simply just not going to be used. And this was one of the very key takeaways for our work itself, and something I wanted to just show you on this slide. This was very early in our work when we were creating sort of landslide impact risk maps. And again, usually I do this in person, so I would ask people to raise their hands, but I'll just assume you're all raising your hands at home to the question of why would this map of landslide risk be hard to interpret? And to me, I thought actually it made a lot of sense. I mean, you can see the dark colors represent, low risk, and then red, to me, red means bad. Okay, so that we're increasing in risk, and then we get to very high risk. But actually, it was very difficult for our end users in Nepal to interpret this map. And that's because how do you differentiate as a policymaker or as someone that's going to make decisions about where to allocate resources in a region that has medium risk versus high risk, or in a region that has high risk versus very high? When we were working with our stakeholders on creating these AI tools and developing these maps, for them, it was very difficult to decipher value in terms of saying, yeah, no, this is a more high risk region versus a medium region. So actually, let's allocate resources to this versus this, because in their eyes, if something's been flagged as an increased risk of landslide, it should all be treated as the same. So where I thought originally maybe having, a scaled version of risk as a would be valuable according to, the probability outputs of our AI model, actually this made it even harder for our stakeholders to interpret. And in the end, we changed actually to a binary map of low risk and increased risk. And this got more positive feedback. I think this figure in general overall also is, I'll be honest, quite ugly. We made it much, much nicer, made the maps look a lot better. This is quite pixelated, things like this, that maybe you don't think about when you're an AI researcher, like how do I make my figures and my maps look very, very nice? But if you work in geospatial AI, of course, you think about these things all the time. And so that's just one takeaway I wanted to note as well. One thing that we had run into a lot as well during our forecasting project, but then also we can consider it as well in terms of data availability from the internet connectivity project, is just the difficulties and challenges that come with data availability and outages, particularly when you're using free resources and you don't have your own sort of infrastructure or can rely on your own satellites, things like this. So what happens if data is not available? What data do you actually need? Something, especially as a PhD student, that I didn't consider or really think about when I was developing my initial proposals is what funding bodies are supporting your project, and is this going to impact what data you're allowed to actually use? This is something I think a lot of people run into maybe as they move more into a more of PI role or a higher academic role, is you're supported by a certain funding body, and there could be a variety of different data products you could use for a certain project, but ultimately there is other factors, political factors, that could be kind of shaping how your research forms. So this was something that we ran into during our project from a data availability perspective and also an outage perspective. We were using freely available data, and halfway through our sort of operational cycle during 2024, we had a data outage and we had to scramble to find a updated or a different data set to use. And we thought we were using very stable data sets, but anything can happen when you're doing operations. So that's just something for a food for thought as well. And then the final sort of lesson learned and thing to think about when you're considering operationalizing for disaster preparedness, but also again, internet connectivity, was usability and logistics. Particularly in this disaster preparedness context, I was building a tool that was then given to the stakeholder in the region for them to generate the landslide risk maps throughout their kind of monsoon season when they wanted to generate these maps. So how do I train these end users to ensure that they can use the tool and I don't need to be constantly on call every time they want to use it, especially if you want someone to like run something every day? How do you train end users so that also if issues do come up, they can kind of solve them themselves, or they can also just interpret the results and act as your sort of champion on the ground in using these tools. Something I think that's very important to think about when you're considering deploying this technology as well is what tech is used to support the AI tool. So are they going to, are folks going to need GPUs or internet connectivity access themselves in order to actually run these tools? If they do, this could be a blocker to actually being used in operation. Speaking of blockers, what exists to fully automate the AI tool? If they are, if the model is being run throughout time and they need to grab the latest data, does the user need to generate new samples? Is this happening on the back end? Things to think about as well when you're operationalizing AI tools. And sort of the final one, and this really kind of goes back to the main purpose of this project as well, is how can we build on pre-existing anticipatory infrastructure or pre-existing infrastructure in terms of what data is collected, how is the data collected, et cetera. I think often we can think of, we building this really complicated and amazing AI tool, and it uses all of this different data, and look how great it is. And the results are amazing, but ultimately, if it doesn't integrate well to the pre-existing ecosystem of a current end user's needs and end user's infrastructure, then ultimately it's just going to be a really cool tool that sort of collects dust, preferably on the internet, or collects dust as a printout or something like that. So that was something that we thought about as well. And the purpose of this project to leverage the pre-existing data impact online portal that they already had in Nepal, use that as our source of truth, and follow the same sort of methodologies in terms of how they're defining what risk means, so that this can be the most effective tool for them. And again, this can also be used as well in the internet connectivity project. How do you train end users to use the data, and also how are you using the pre-existing infrastructure in that region in terms of their internet connectivity labels. Okay, and with that, I just wanted to say thanks very much for your time. I know the two projects were quite different, but I hope to provide some synergies between the two. And of course, thank you to all my collaborators on this. This was a very exciting project, the Giga project, to work with UNICEF and ITU and the ESIF Lab. And thanks very much.
Okay, thanks. Thanks very much for the very nice and insightful presentation. And let's open the floor for questions. And we already have a few questions from the neural network. And let's start with this one from William Locker. They said they assumed embeddings were designed to work with deep learning models. But here, only MLP was tested. And they are wondering that do studies tend to use embeddings with traditional machine learning like random forest, or deep learning models like CNN, or both? And do we know if there is a better performance with one or the other?
Yeah, that's a great question. Actually, the reason we ended up moving forward with the random forest and gradient boosting and these machine learning classifiers was because our features were in a tabular format. And we've seen in previous works that actually kind of standard ML classifiers either perform on par or quite similarly to deep learning models. So we're extracting our embeddings per point, but we are essentially treating those embeddings as a feature vector. So for example, we have that 256 embeddings as opposed to using a deep learning model. That's traditionally why we used it. And also we wanted to provide that sort of more interpretability in terms of that feature importance. That's not to say that deep learning should not be considered at all, and definitely a part of the future work of the project, as well as to use other different architectures to explore this.
Okay, thanks. Actually, I also have one follow-up question about the embedding. So when you move from manually engineered features to the spatial embeddings, so the notion of the buffer size, I think, it's become less explicit. It's no longer about averaging within a fixed radius, right? But about what the model can see spatially. So do you have a sense of what scale it ends up learning from, or how do you interpret that afterward?
Yeah, that's a great question. I don't have the numbers on the top of my head now, but it would be essentially, the scale would be driven on whatever the scale of the data set that the model was trained on for the embeddings. So for example, for Sentinel-2, I believe that's around 10 meter. I believe the Sentinel is from 10 to 16 meters. So this would be a much smaller spatial extent as opposed to using like functional map of the world or other ones. But I don't know those spatial extents off the top of my head. And this is why I think the combination of the embeddings with those geospatial buffer information actually performed much better, because now you're getting, a 10 meters surrounding a school is not really going to capture the same spatial context as having that like 1,000 meter buffer. So that's why we felt that the combination actually was the best to do that way. But I'd have to dig up the actual numbers of the spatial extent for the embeddings itself.
Okay, thanks. And there is another question about the uncertainty. So given the possibilities of almost identical schools to have the different outcomes, do any of your models provide uncertainty measures?
We're not using uncertainty in the traditional sense. So actually, my other project I didn't include is sort of a benchmark of uncertainty. What we did do was we ran every single model at least 5 to 10 times, and we had varying the validation sets so that we could have a sense of the variance in the predictions itself. I didn't include those numbers. They were pretty low, but outside of that, we didn't include uncertainty. I think this is actually a big gap for more like a global approach that could definitely be drawn upon. This work as well is on Archive as a preprint, so definitely encourage folks to check it out. And if they want to discuss like future work on this too, I'd say I'd be happy to chat.
Yeah. And one more question about the type of the connectivity. So they are wondering, when you talk about school connectivity, do you mean cellular internet, Wi-Fi, or both? And did you use any data directly from mobile network operators?
Yes, so we refer to internet connectivity as whatever is reported by the school. So it could be different in terms of like wireless or like Ethernet cable, for example. But that's what we're focusing on. We're not focusing on mobile internet connectivity. So this is via like you have like your actual in the school, you have your measurements of your bandwidth and upload speed, download speed. Not all schools provided actual speeds, so this is why we ended up going with just a binary classification of yes connected or no not connected, as opposed to doing like which ones had high speed internet versus low speed internet. We did use some mobile information. We used Ookla speed test data, so this is also a free data set that you can get online as well if folks are interested in this type of research. So we used those types of, I'm trying to search on my end what I used. I have a map, but I don't have it. Oh yeah, here we go. So I used Ookla speed test data. So download speed of mobile devices in the nearest tile that the Ookla data has. So upload speed, latency of mobile tests. So we did have mobile information, but again, we're looking at the actual school infrastructure itself. So this would be more like Ethernet, wired, wireless. But we did use the mobile data. Yeah.
Okay, thanks. And yeah, one audience is very interested into your AirPi package. So they're asking, did you already test, deploy, and adapt your AirPi package on the ESA Dunio platform?
So AirPi is actually available on GitHub, so you can get it there. It was actually developed when I was at NASA, so I used it during this ESA project and this UNICEF project, but I developed it prior for my other climate projects. So if you Google just like GitHub AirPi, you can get access to it there. I'm hoping to also provide a little bit more new data supporting more data sets. Just been quite busy with new job and finishing PhD and all these things. But yeah, feel free to reach out as well to myself if you have any questions about using AirPi or have any interest in other data sets supported. It's pretty easy to add data sets once you have as well if you wanted to fork the repository yourself and add other tech.
Okay, yeah, thanks. So yeah, I also have one question. So I noticed that you use the auxiliary data sets, like the educational level, distance to the UTM station. That seems help the model a lot. But I was wondering, where is the line between the useful contextual information and something that just make the model depend on the existing infrastructure maps? So how do you make sure it's really learning some transferable relationship rather than picking up the correlations that wouldn't hold elsewhere?
Yeah, that's a great point. And I think a lot of this can more sort of be answered or revealed in a like a feature ablation study. I think one thing we wanted to avoid doing, but has been done in the past, is regional indicators or regional information, because this kind of biases the model right away, right? You can think
Mm,
about probably schools that are in a city are more likely to be connected to the internet than more rural schools. So if you're inherently baking this information into the model itself, that something in the capital city versus something in a more rural region is like a more important piece of information, then the model is going to be more biased. Our idea was just to explore like, okay, what auxiliary information do we have at all from the pre-existing database? Let's throw it in and see like how far we can push performance. But I think you're absolutely right. We can't, at that point, then you might always just be pointing the model to like, yes, in city, therefore connected to the internet. And I think this is also where you can look at splitting your data set geographically and training, maybe on certain regions and then having your held out test set on others such that you can sort of capture if it actually is truly being biased. So that would be one way to do it itself. At the time, we were mostly just trying to explore like of all of the data we can possibly get our hands on, what actually improves performance just like objectively.
Yeah, so I also also noticed that the model have the false positive prediction, right? So
Mhm.
I'm very curious, are these predictions reliable enough to guide specific investment, or are they meant more for the regional level planning?
It's really up to the country offices in the end, I guess, how they use the information. We were just trying to provide a way that was essentially free and or cheaper to do it. The sort of end user also would be like internet service providers in the countries itself as well to essentially give like targets or regions of development because ultimately like business runs the world. So we're trying to provide like a business case for the internet's service providers to be able to target these regions that are sort of like areas where they can then develop and
Mm,
build that internet infrastructure itself. So that was kind of the sort of end user case, but it was really up to sort of the country offices to kind of make final decisions about how they use their data, which also kind of goes back to what I was talking about in terms of like usability and communication. It's really in the end you can try to design a tool however you want and provide the information you think is important, but it's up to really the communication with the stakeholders, understanding what they actually can use the information to do or what actionable information is provided in the end. Yeah.
yes. And yeah, I have another question. So I think when the new schools come online, so the connectivity also change very quickly. So how can you keep the data and the model up to date?
Yeah, I think for that, in terms of if it's in operation, this is just going back to like a retraining schedule and having this a part of sort of the maintenance of the tool itself. And again, this kind of also just goes back to the communication to the stakeholders because there's always going to be some latency between when a school is connected and then when actually
Mm,
that is communicated to the end user or ourselves actually. So that's just going to go back to sort of having those communication links quite strong. I was quite far on the other end because I was a PhD student, so I'm not the one that's directly sort of on the line with them. So I'm more relying on sort of like the project managers and things like that. But it would just be more so of having like it baked into the schedule of the tool itself to automatically retrain the model. And that's also for our disaster preparedness tool as well. We had a part of the operational sort of life cycle of
hmm.
at a certain amount of time. Okay, now we take, it's the tool's offline for 24 hours. We do a retrain, etc.
Okay, so after your model was deployed for the operational use, did you get any feedback from the end users?
We did. I can't really talk about for it because it's a part of the paper we're about to submit, so that's why I didn't include it. But
Uh-huh.
I mean, it was positive, so that's good. I mean, I think one of the biggest ones was again going back to that map I showed of like why is this hard to interpret? So that was like kind of the original version of our tool, and that was the original feedback we got was like, okay, we understand what you're trying to achieve here, and the conversation was had with the stakeholders about even using these colors and things like this at the beginning. And then it was when we did our retrospective post operationalizing, we're like, actually, when we printed these maps each week and disseminated this information, the feedback we got was, what do you mean high versus very high risk? How do we actually allocate resources accordingly then? And that's how we ended up changing our model or not changing the model, but sorry, changing the communication in the end to being low risk and increased risk because this was able to be more like clear and communicative and able to actually make decisions from. So that was one of the biggest sort of takeaways from that was making things as simple as possible so that people can make decisions from it.
Yes, I think it's moving from research to something operational is always hard. Yeah.
Totally. Yeah, especially as a PhD. But it was very fun. And I encourage folks to explore it if they're in their research journeys as well. It's very impactful and can be very, feel very good to be able to do that as well.
Okay, nice. Okay, I think now we are coming to the end of our time, and I want to thank Kelsey again for sharing the work and insights, and thank to all of you for joining and contributing your questions. And with that, I think we can close today's session and hand over to the outro video. Thanks, Kelsey.
Thanks so much for having me.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.